Dyadic product of vectors. The dyadic product of two vectors A and B, denoted as AB or A dyadic B, is defined as a transformation that maps any vector C according to the following rule. The dyadic product of vectors A and B acting on vector C equals vector A multiplied by the dot product of vector B and vector C. Is dyadic product AB classified as a tensor? Indeed it is. To verify this, let's analyze it as follows. For any vectors C and D and any scalars alpha and beta, using the definition 1, we have the dyadic product of vectors A and B acting on alpha C plus beta D using equation 1 is equal to A multiplied by the dot product of vectors B and alpha C plus beta D. It is equal to A multiplied by alpha B dot C plus beta B dot D. The vector A is distributed to the bracket. Using equation 1, it is equal to alpha dyadic product of A and B acting on C plus beta dyadic product of A and B acting on D. This confirms, as explained in the video number 10 shown at the top right, that the dyadic product AB behaves as a linear transformation and thus qualifies as a tensor. Next, let's discuss the components of the dyadic tensor AB. Consider tensor W defined by the dyadic product of two vectors A and B. The components of W defined as Wij are determined as Wij is equal to Ei dot Wij. As explained in the video number 11 shown at the top right. Using equation 3, it is equal to Ei dot Abej. And using the definition 1, it can be written as the dot product of vectors Ei and A is equal to Ai, and the dot product of B and Ej is equal to Bj. So it is equal to Aibj. Therefore, Wij is equal to Aibj. This allows us to express the tensor W in a convenient matrix form. Matrix representation of the dyadic tensor AB. Using equation 4, the matrix representation of W is alternatively, W can be represented as, we call this the matrix representation of the dyadic tensor, dyadic product of the base vectors. The dyadic product of base vectors is crucial as it creates fundamental matrices essential for clearly representing tensors, physical transformations, and vector interactions, simplifying calculations across physics and engineering. Specifically, the dyadic product of the base vectors Ei are how to represent a tensor in terms of the base vectors. Using equation 7, it is evident that any second-order tensor T can be represented as Using the Einstein summation convention, equation 8 can be compactly expressed as This approach extends naturally to higher-order tensors. Higher-order tensors. A third-order tensor T can be represented as and similarly for tensors of even higher orders. Such tensorial representations are essential because they simplify handling of coordinate transformations and tensor operations and provide insight into various physical phenomena such as those encountered in continuum mechanics, mechanics of material, and relativity. With this fundamental understanding, you are now equipped to explore further applications of tensors in continuum mechanics. Thank you for watching, and we will see you in the next video.